Jai Hind all. This is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College. This is a lecture series on satellite communication, and we are discussing the complex topics, the topics beyond the syllabus of AKT. In the last series of this complex topics, we are discussing design of satellite links. We have discussed the link design in the main topics, where we have discussed the uplink design and the downlink design. We have discussed the link equations. In this lecture, we will discuss one of the example of this design link, how link design is calculated for the uplink as well as for the downlink, downlinks, and then how the overall uplink and the downlink design is estimated, that is we will discuss. So design of a satellite link. Satellite link is probably the most basic in the microwave communication, since the line of sight path typically exists between the satellite and the space only. This means that the imaginary line can be extended between the transmitting and the receiving earth station. The satellite antenna passes only through the atmosphere and not the ground obstacles. Such a link is governed by the free space propagation, with only limited variation with respect to the time due to the various constitutions of the atmosphere, for example, clouds or the extraterrestrial bodies. Free space attenuation is determined by the inverse square law, which states that the power received is inversely proportional to the square of the distance between satellite and the earth. The same law is can be applied to the amount of the light that reaches to our eye from a distant point source, such as an automobile headlight or a star. There are, however, a number of additional effects that produces a significant amount of degradation and the time variations. These different effects include rain, terrain effects such as absorption by trees or walls, and some low obvious impairments produced by unstable conditions of air and ionosphere. If we discuss the links, then we have two links. One is between the earth station to the satellite, and other is the satellite to the earth station. The earth station to the satellite link is called uplink, and the satellite to the earth station is the downlink. If we see the total block diagram of the satellite, it can be seen like this one. In the initial phase, some information is inputted, which is encoded, then modulated up then up converted, then high power amplifier is used to transmit it through the antenna toward the satellite. Satellite as a space relay or space repeater, it will repeat the transmit, regenerate the transmit, and transmit it toward the earth station. At the earth station, there will be low noise amplifier, then the receiver and demodulator will be down converter, and the demodulator will be there, and last decoder for the information receiver. So there are two links, one is the uplink and other is the downlink. So if we see the downlink design, the figure that is previously shows a large hub type earth station in the uplink and a small VSAT in the downlink. The satellite is represented by simple frequency translating type repeater. For example, we have used only a bent pipe transponder. Most geostationary satellites employ bent pipe transponder repeater, since these allow the widest range of services and the communication techniques. Bidirectional communication occurs with a separate transmission from each earth station. Due to the analog nature of the radio frequency link, Each element contributes a gain or loss to the link and may add noise or interference individually. The result of overall performance is presented in the terms of the ratio of signal to the noise, temperature or the power. The signal power can be taken as a carrier power. So because most of the power is taken by the carrier in the transmitted link. So we generally calculate signal to the noise ratio as we have discussed it in the main lecture series. Ultimately, the information quality, that is bit error rate or video impairments or audio fidelity, will be affected. Done properly, this analysis can predict if the link will work with stationary quality based on the specification of the ground or the space component. The uncertainty can be covered by providing an appropriate amount of link margin which is over and above the C by N needed to deal with propagation effect and non-linearity in Earth stations and satellite repeater. The link design can be taken from the powers of the transmitter and the received signal. The link between the Earth station and satellite is governed by the basic Friis equation, which gives the received power is equal to the transmitted power, the gain of the transmitted antenna, gain of the receiver antenna into the speed of the light into 4 divided by 4 pi square r is the distance between satellite and Earth station square and the f square, where PR is the power received by the receiving antenna, PT is the power transmitted by the transmitting antenna, GT is the transmitted antenna gain, GR is the gain of the receiving antenna, C is the speed of the light, approximately 3 into 10 raised to power 8 meter per second. R is the range between the satellite and the Earth, so it is generally in meters. And last is the F is the frequency in the hertz of the uplink or the downlink. The PT-GT is also called the EIRP of the signal. The the term PT-GT, the transmitted power into the transmitted gain, antenna gain, is also known as the effective isotropic radiated power. So almost all calculations is performed after converting the product into the decibels, because most of the powers are low, so we have to convert it into the decibels. Same formula can be converted into decibels by which can be taken as a balance from the, like, PR is in dB. PR is equal to P plus PT plus GT plus GR minus of 20 log of F into R plus 4.76, which is the log of 4 pi square. So this is multiplication. PT, GT and GR multiplication is converted into addition, as they has been converted into dB. So all these have units of dB, whereas in the previous case all these have the units like meter per second or meters, etc. So all these things are converted into the decibels. Then the received power in this formula is measured in decibel relative to 1 watt, which is stated as dB. The last two terms presents a free space loss between the Earth station and the satellite. If we assume that the frequency is 1 and the distance is taken for simplicity geostationary satellite, which is approximately 36,000 or 35,786 kilometers, then the path loss can be taken as path loss in dB will be 183.5 dB. So the complete equation can be as PR plus PR is equal to PT plus GT plus GR minus 183.5 dB. Now here we have taken as 1 gigahertz as the frequency, and the radius, the height of the satellite is 35.788 kilometers. Now we can correct the path loss for other frequencies and path lengths using the formula the previously given as A naught is equal to 183.5 plus 20 log of f plus 20 log r divided by the radius, total height of the satellite, where A naught is the free space path loss in decibel, f is a frequency in gigahertz, r is a path length in the kilometers. The term on the right can be expressed in the terms of the elevation angle of the earth station toward the satellite. All these terms. So in terms of the terms on the right can be expressed in terms of the elevation angle, which can be represented as r is equal to the radius, total radius of the geostationary satellite divided by 1 minus the angle between the satellite and the earth station at the center as well as at the ground center. So we can say that this phi on the psi are the latitude, phi is the latitude and psi is the longitude of the earth station. So this station minus that of the satellite, for example the relative longitude. This can be clarified from this figure. Here this is the angle theta, and angle between is the difference between these two satellites. So substituting the r in A naught, we can obtain the correction term in decibels to account for the actual path length. This is referred to as the slant range adjustment in and a function of the elevation angle theta. So this is the diagram which can show that when we are calculating a link budget, we are taking r from here to the radius, but we can take this r the height of the satellite from the earth station, then there will be some difference. So to calculate this difference, we need a slant height. This slant height is known by the r. So slant range distance is r between earth station and the geostationary satellite. The earth station elevation angle is this theta with respect to the local horizon at the ground station. So with this one, if we increase this slant height, then we can see that the ground elevation angle as the path loss will be increasing as this additional height will be increasing, slant height will be increasing. So we can see that initially the elevation angle is low, the path loss is more when the path loss is less at the 90 degrees. So that means at the 90 degree, this slant range will be at the approximately at the in front of the satellite directly. So as it is moving away from the footprint of the satellite at the center of the earth, then it will be creating more slant range losses. And another interpretation can be taken from the this frequency table and the effects from the table. If we see the Faraday rotation with the change in the frequency from 100 megahertz to 10 gigahertz, we can see that there is 30 rotation to 1 degree rotation, that is Faraday rotation. So there is a rotation of the linear angle polarization with the change in the frequency. Another access time delay, we can see that it is approximately same, but for the some of the frequencies it is lower. So it is going down with the increase in the frequency. Then absorption in the polar, it is also going down in dBs with 5 to 0.005 dB. Then absorption in the case of the mid latitude, it is again less than 1 dB, and for the 10 gigahertz it is 0.001 dB. Then depression is going from 1 Pascal per hertz to 0.10 raised to 4 into 10 raised to power minus 6 Pascal per hertz. So with this, all conditions are generally taken with the no attenuation due to the ionospheric or the atmospheric effects. If we calculate also those, then we have to include some of the ionospheric effects. These are the Faraday rotation, time delays, refraction, and the dispersion. It is clear from the previous table that ionospheric effects are not significant at the frequency of the 10 gigahertz. However, it is more in the lower bands, so it must be considered in the L band, S band, or C band. The tropospherical effect, or we can say that the gaseous atmospheric effect, the absorption by the air and the water vapor, non-condensed water vapor, this is not consistent for the higher elevation angles. Adding only a few tenths of the decibel to the path loss, it is generally can be ignored at the frequencies below 15 gigahertz. The refractive bending and scintillation, rapid fluctuation of the carrier power, is called the scintillation. So the refractive binding and this fluctuations at the low elevation angle, earth station that must point within the 10 degree of the horizon to view the satellite, are the subject to wide variations in the receiver and the transmitted signal, and therefore required more link margin. This tropospheric scintillation is the time varying signal attenuation and enhancement caused by the combination of the direct path between refracted path signal in the receiving antenna. Rain attenuation, the most important factor caused with the frequency and the rain rate. Additional feed margin is required for the Ku and Ka band links based on the statics of the local rainfall. This will require careful study for service that demand high availability as suggested in the next figures, and a standardized rain attenuation prediction, that is called DAH model, is available for this purpose. Rain also introduced scintillation due to the scattering of electromagnetic waves by raindrop, and in the later section we will also see that these raindrops also radiate thermal noise, a factor that is easily modeled. In addition, rain bending on antenna surface scatters in the very heavy rain that can paddle the feet, temporarily provided high losses not according to the DAH or the thermal noise models. So if we see the downlink budget, the following table represents an example of the link budget. The budget in manner that identifies the characteristic of the satellite transmitted and the antenna, the path, receiving antenna, and the expected performance of the earth station receiver. It contains the elements that select the desired radio signal, and demodulates the useful information, that is the baseband signal. for example the video signal. Once converted back to the baseband signal, the transmission can be applied to other processes such as demultiplexing, decryption, or the digital to analog conversion. So in the downlink, we need the transmitted power transmitted, the transmitted wavelength loss, then the attenuation gain, then satellites EIRP, then free space loss, then atmospheric absorption, then receiving station antenna gain, receiver waveguide loss, received carrier power, system noise temperature, earth station, G by T ratio, Boltzmann constant is known, bandwidth, noise power, and carrier to the noise ratio is required. All the values are given here are typical values with the units in dB. So when we are using Friis equation or using the link equation, we have to add or the subtract all these equations. So this following figure, the figure of this one provides the horizontal downlink coverage of one satellite known as the Telstar 5, a typical C-band satellite that serves the United States. Each curve shows a consistent level of saturated effective isotropic radiated power, the value of saturation of the transponder power. Assuming the receiving earth station is in Los Angeles, it is possible to interpolate between the contour and estimated value of 35.5 dB watt. So these are the coverage footprints of the Telstar 5. These curves indicates that the saturated EIRP decibel refers between 1 watt. So this is the footprint of the Telstar 5. So the following parameter, now we have discussed the downlink. Again, if we see the following parameter related to the significant elements in the link, the power balance equation all expressed in the decibels. The most typical under control of the satellite engineers is the transmitted power, antenna gain, maximum antenna gain at the beam width of the 3 dB, the feeder waveguide loss, the EIRP in the direction of the earth station, the received noise power, and the noise figure. The system noise temperature is the sum of the noise temperature and the noise contribution of the receiver antenna. The overall earth station figure of merit is defined as a ratio of received antenna to the system noise temperature expressed in the decibel per Kelvin, for example GT. The same can be said of EIRP for transmit case. Reception is improved if either the gain is increased or noise temperature is decreased, hence the use of the G by T ratio. Each of the link parameter relates to the specific piece of the hardware or some property of the microwave path between the space and the ground. The good way to develop the link budget is to prepare it with the spreadsheet program. This permits the designer to include the various formula directly in the link budget, thus avoiding the problem of external calculation or potential for arithmetic errors. There can be still some errors, but that can be minimized with the help of these formulas. Commercial link budget software such as Setmaster Pro from the different services does the same job but in the standardized fashion. So this is the uplink budget where we have transmitted power given, the transmitted waveguide loss, transmitted antenna gain is given, uplink EIRP from the Boston place is given, spreading laws are given, arithmetic attenuation are required, then flux density at the spacecraft, free space loss, receiving antenna gain, then receive waveguide loss, system noise temperature, the spacecraft signal to noise ratio, the receiver carrier to the noise temperature, Boltzmann constant, the bandwidth, and carrier to the noise power are required. All these values are given are the typical values, and these values are in the dB. The uplink, the coverage footprint of telstar at the located at a particular location, the different contours with SFDM in the direction of the Earth can be is shown here for the reference. The repeater in this design is simple bent pipe that does not alter or recover the data from the transmission from the uplink. The noise on uplink n in the denominator, that is C by n ratio, will be transferred directly to the downlink and added to the downlink noise. The baseband processing type of repeater, the uplink carrier is demodulated within the satellite and only bit themselves are transferred to the downlink. In such case, the uplink noise only produces bit error that transfer over the remodulation carrier. There are few possibilities that frame errors are also introduced depending upon the modulation and the multiple access schemes. This is a complex process and can only be assessed for the particular transmission system designed in the digital processing satellite. When we have calculated the uplink budget and the downlink budget, the last step is to calculate the overall budget. The overall link budget means the uplink as well as the downlink. The last step for the link budgeting is for a band pipe repeater is to combine the both uplink and the downlink performances and compare the result against the minimum requirements. These minimum requirements are called the threshold. A typical value of all these threshold are presented in table 2.5, which presents the detailed evaluation of the overall link under the condition of the line of sight propagation in the clear sky. We have included an allocation for the interference coming from the sources such as the cross polarized transponder and adjacent satellite. This type of entry is necessary because all operating satellite networks are exposed to one or more sources of interference. The bottom line presents the margin that is available to counter rain attenuation and any other losses that were not included in the link budget. Alternatively, rain margin can be allocated separately to the uplink and the downlink, with combined availability value being the arithmetic product of the two as a decimal value. For example, if we uplink and the downlink were 99.9, then the combined value is 99.99 into 0.99 is equal to 99.8%. So this table 2.5 shows the typical values of the overall link. For example, the uplink C by N ratio, the noise to the carrier ratio, then downlink carrier to noise ratio, then the overall noise to the carrier ratio, the total thermal noise, the total thermal C by N ratio, the total thermal C by Nth ratio, the interference C by I, carrier to interference ratio, interference to carrier overall ratio, then total noise, then total C by noise plus I ratio, then total C by N ratio, and the required C by N ratio. The typical values are given here and all these units are in the ratios. So here in this lecture we have discussed the overall specifications of the link budget. We have discussed the downlink budget example and then an example of the uplink budget. From all these uplink and the downlink examples, we have calculated the overall link budget. Thank you.